So as an example of input-output automata, we describe an asynchronous network system. So we first describe the component types of this system, and later we show how to combine components into a complete system. An asynchronous network system consists of asynchronous network, which is processes that communicate via channels. So these are the processes, and we have here the channels. So the channels are unidirectional, so it means if this is process P1 and this is process P2, we have two channels, one from P1 to P2 and the other from P2 to P1. So processes and channels are reactive components that interact with their environment via input-output actions. That's what we are going to show. And they are modeled by input-output automata. So here we have our automata. We have 4 automata, process P1 and process P2. And then we have 2 directional channels, one from P1 to P2, which transfers messages from P1 to P2, and one which transfers messages from P2 to P1. So let us look to a process here. So process, for example, P1 will have 2 input actions. This is one input action, and this is the second input action. The first input action, it's an input from the environment. In this case, the environment wants to give process P1 an initial value V. And here we have an input action from a channel. This is the channel C21, which is an input action that is the delivery of a message M from process P2 to process P1. These are input actions. A process also has 2 output actions. One action is giving a result back to the environment, and we call this a decide specific value. So this is some kind of agreement protocol between the environment and the processes. So that's an output action. And also a process like P1 can send a message to process P2. So this is an output action, which is sending a message. So the same holds for P2, but let us look to a channel. So if we look to this channel, so it has an input action, which is the send here, and it has an output action, which is the delivery of a message. So this will deliver a message from P1 to P2. So now let us describe each component separately. First, the channel automaton. So let's see what's the channel. You can see what's the channel here. In this case, we are going to model a reliable unidirectional FIFO channel between 2 processes. It's unidirectional and FIFO, so it keeps the order of message. The message that is sent here will be delivered in the same order. It has a fixed set of messages. This is called M, and it has a signature, and the signature for input actions. So it is a set of all send M, where M is element of capital M, the set of all messages, and the set of output actions, which is deliver M. So it's a set, it's deliver M, where M again is an element of the set of all messages, and it has no internal actions. So this is the signature of the channel automaton. So this channel has a state. And what is a state? The state in this case is a FIFO queue of elements of M, and it's initially empty. So now let us look to the transitions. And we are going to describe the transitions by what we call transition definitions. So this is, for example, is a transition definition. It looks like a procedure, but actually it defines a set of transitions. So we have one transition called send M. This transition is the action performed when the input automaton performs the send action. And this one here is called a deliver transition definition. And the task, all delivers action, is one task. So whenever we perform an action, so all these deliver actions are basically one task. But let us try to understand these transitions. So the description of a transition definition is as follows. A send M has an effect, and the effect is add a message M to the end of the queue. That's what it does. And that's an input action. So let us look to an typical output action, which is in the deliver here. It has first a precondition, and the precondition says you will deliver M only in the case that M is the first or the head of the queue. And the effect is to remove M from the queue. So this looks like code. As we said here, transitions are described using transition definitions, which are little code fragments. Each one of these transition definitions defines a set of transitions. So let us look to one transition. What is a transition here? A transition should have some state. We call it S, perform an action A, and the resulting state, let us call it S prime. So what is this send is saying? Send is saying if the state of the queue, say it is called queue, and you perform a send M, then the resulting state, we call it Q prime, will in this case be the previous state of the queue, but adding to the end the message M. That's what it says. So this is basically defines a set of transitions. That's why we call it transition definitions. And let us look to the deliver. So the deliver has a condition which says that Q is not empty. And it basically says if Q has this form, the form that it has a message M, this message M, followed by the rest of the queue, Q prime, then the effect, then the result is Q prime, basically. Okay? And M will be the message that is going to be delivered. It is in the head of the queue. So that is basically the description. So even you can see it as code, it is not really code. It describes this set of transitions. So as we said, now transitions are described using transition definitions, which are called fragment. And each transition definition describes a set of transition for the corresponding action. So, and they are grouped by the action type. To define our system of two channels and two processes, we add subscripts to indicate particular endpoints. So for example, for process PI, if it is sending a message to PJ, then the action will be send M, IJ, and the channel will be C, IJ, and the delivery will be deliver M, IJ. That's what we mean by adding subscripts to a particular endpoint. So here the channel is used to connect process PI and PJ. For channel CIJ, we have the set of actions send M, IJ, and the set of deliver M, IJ, where M is the head of the queue, and the effect on the state is to remove M from the queue. So now that we have defined the FIFO channels, let us define, just as an example, a process, okay? As an example, as an IO automata. So what we have here, we have a process, we call it PI. As we said, it has two input actions, init and deliver. Deliver comes from the network, init comes from the environment, and PI has two output action. It sends the message and then it delivers some decision to the environment. Let us see what we want process PI to do. Process PI defines a simple agreement protocol, a very simple agreement protocol. And what is that agreement protocol? Inputs arrive from outside, that's what we call the environment. And each process, for example, process PI, sends and receives through delivery values and collect a vector of values, one element for each process. So if we have in the system 3 processes, so PI has a vector of 3 elements. It has its own element, we call it element I, and then it has one element for each other process. Initially, the vector is empty or undefined. But when the vector is filled, the process outputs a decision obtained as a function f on that vector. So initially, the vector is empty. Its external environment through init will initiate one of the elements here, and the other elements will be communicated by other processes. And once such a vector is filled, the process will perform an output action, which is decide, which is a function of that vector. So a process can get new inputs. These inputs can change value and can send values through the send and can output decisions repeatedly. So what we have as tasks here, we have sending to each individual neighbor is a task, and outputting decision is another task. So here is our process. We looked for the code for process PI. This process will have inputs. And what are the inputs? The input is init vi from a fixed set v. That's this one. For each process, we have a channel which is called deliver ji. So if it is between process P1 and P2, so it will be deliver from, say, P2 to P1. If this is process P1. And what is deliver? It has, again, v is element of the fixed set v of messages, that values that are sent. And we have these deliver for each j that is not I. It means there is a delivery input from all processes through their channels. So that is input. Then we have output. Similarly, we have a decide output, value v, and we have a send, which communicates send I to j, means process PI is sending a message to process j. And this also, again, to all other processes. That's why it's for all j that are not equal to I. So what is the state of each process? It has a local state. And the state is as follows. It's called a vector called val. And the vector is indexed by 1 to n, and n is a number of processes. And initially, the vector is empty, and this is a notation for empty or null. So the set that these elements can assume is from the values, the set v and the empty value. Let us look to the transitions of each process. So what does a process do? So when a process interacts with the environment by init, so it gets from the environment, this is an input action, it gets from environment the value v, so it assigns the value v to its position in the vector. When it gets from the network or the channel a value v, this is the value coming from process pj, then it assigns the element j in the vector that value that it just got. So now we have dealt with the input. Now we are going to deal with the output. And remember, outputs are very interesting. They have preconditions, as you can see here. So ascend has a precondition, and this side has a precondition. So let us see what is ascend, a value v from I to j means. It has a precondition that the element I, which the element owned by this process, has a value that is not undefined. So this is not this empty undefined value. So that is what is an output action. As you can see, it's declarative. It says it sends v if v is the value of that element in the vector. We have covered the send as an output action. So now we are looking to decide. Decide is just saying whenever the vector as a whole has well-defined values, so none of the values are null, then you are allowed as a process to interact and do an output to the environment which applying the function f to that vector. And the effect, there is no state changes here. So this process is somehow does not change state. The changes of the state happen from interaction with the network or interaction with the environment. So this ends a description of two automaton. One is the process automata, the other is the channel automata, and it shows by having these subscripts we can connect things together. So now, given that we put these things together, what is an execution of this system?